Okay, so welcome everybody. It's my pleasure to introduce Claire Vernade. So she's a research scientist at Deepmind, that I guess you all know. And so she got her PhD at Telecom Paritech, and afterwards, at the same time, she was a research scientist at Amazon and the University of Magdeburg. Her main research interest is in sequential decision making, and today she's going to talk about non-stationary delayed bandits with intermediate observation. So welcome, please. Thank you.
Thank you. So good afternoon, everyone. Thank you, Sylvia, for the invitation and for the kind introduction. It's really a pleasure to be here to present this work. So this was a paper that was accepted and published at ICML in 2020. And that due to the situation, I didn't have that much occasion to actually present. So it's really a pleasure to be here in front of real people to show a little bit what we've tried to do back before the pandemic happened. So this is a joint work with András György, my colleague in the foundations team, and Timothy Mann, who works for the Deepmind applied, like Deepmind for Google kind of department. And he came to me basically when I started at Deepmind. And he was like, I have this problem. I currently work for app recommendations like Google Play Store. And the problem is the following. I have customers with changing preferences, like they tend to change their mind about what they want to do, what app they want to install, and what things they want to see. And I need to optimize for long-term metrics, which are like reviews or app or purchase on an app, or like in his case, it was actually like app usage. Like he wants to recommend an app that someone is actually going to use for the next 2 weeks. So at the end of 2 weeks, we measure how much the app has been used, and we say, okay, this is a good app or this is a bad app. But so before that point, we actually have no feedback for our recommendation. So this is a ubiquitous problem in recommender systems. The feedback, the metric that we optimize are long-term by design. And the problem is that the customer preferences are changing. So during these 2 weeks, it's possible that what you've recommended is no longer the good thing to do. So basically, they were facing this problem where they had like actions, or like they were taking actions, and they couldn't really evaluate it. It's not completely true, because like systems, like if that was true, then we couldn't do anything and Google wouldn't be a business. It's not completely true. There is actually a lot of things that you can monitor in the meantime, which are like signals. Typically, did the person download or not? Did they like it? Maybe they shared the content with someone else. I don't know, like a lot of kind of signals that you can record, which are not the reward that you want to optimize for, but they can be used somehow. They are somewhat related, or they may be somewhat related with the reward you want to optimize. So yeah, I had some previous work on delayed feedback and on non-stationary bandits and things like that. So I'm going to unpack all these weird vocabulary words in a second. But basically, for me, it really looked like that. It looked like you have Google, which is an agent, and the agent takes actions, and the environment, which are the customers with changing preferences, which is non-stationary, sends delayed rewards, and with intermediate observations. And I was like, this really, really looks like an RL problem, except that it's a bit simpler. It's simpler because the actions that Google take actually don't significantly modify the environment itself. Like it's not because you're being recommended that you change preferences, or at least in the first approximation, you can neglect this. So you can actually model this problem as something simpler than reinforcement learning that we call the bandit model. So this talk is about how we resolved this problem by introducing a new bandit model. And I tried to design the talk as like kind of a tutorial, like something that where I introduce bandits, I introduce non-stationary problems and delayed feedback problems. And I try to walk you through our attempt to solving this problem. So is there any questions so far? No? Okay, so let's dive into what are bandits. In the first place, because I've been using this word a lot. So a bandit problem is a sequential decision-making problem, where at each round you need to take one of k action. So the agent has k choices, and every time an action is chosen, there's a reward, RT, which is generated by the environment. And this reward is a random observation from a distribution, which only depends on the taken action. Meaning if you take action 1, you don't get any observation about action 2. You only receive something about action 1. And so we make a few assumptions that are very simple. The first one is that we assume that all these distributions have a mean. Like, so don't imagine that it's like heavy-tailed things or like complicated business. Like usually they are bounded or they are like sub-Gaussian or Gaussian distributions. So when you pull an action, basically you can think of it as like sampling from a Gaussian that whose mean you don't know. And this mean I noted theta A for action A. And then I assume that there's one of these actions that is the best. And this is, so I denoted A star. And this is the action that you would like to pull all the time. The problem is that you don't know the thetas at the beginning. So you need to pull the arms to collect data, to estimate the theta, and decide which of these actions you want to take in the long run. So there is this exploration versus exploitation dilemma. Like at every round, you want to take the action that makes the most reward, but you also want to collect information about the whole environment. So your metric, you do all this in the goal of minimizing something that we call regret. So the regret is the cumulative sum of the losses that you've suffered on the way to while pulling your arms. So every time you pull an arm 80, you suffer a loss that is the difference between the mean of the best arm and the mean of the arm you pulled. So when you pull the best arm, you actually suffer 0 loss. And so that's like a very current metric and a very common metric. And so it's an old problem that dates back from, let's say, 1933 or something like that. And so there's been a lot of literature, and basically we kind of know how to solve this problem. And the way we solve it today is using this algorithm. It's called UCB. So I'm simplifying things. There are other algorithms, but I'm going to describe the kind of generic paradigm of how to solve bandit problems or explore-exploit problem like this. So at a certain round T, you ask, what is the next action I want to take? And you have a certain amount of information, which I denote here HT, which is my history. This history contains the actions and the rewards that I've been taking all along the way so far. So HT contains all this, and I can kind of compute summary statistics. So how many times I pulled action A, up to time T, how many rewards I got from action A, up to time T. So these are N and S. And with these, I can compute the empirical average of the rewards for each arm. So because I pulled a certain amount of time each arm, I have some estimate of what they're worth. But so these estimates here, I denote theta hat. So theta hat for arm 1 and theta hat for arm 2. But okay, I'm going to speak louder. So the problem is that there is some uncertainty, right? Because you don't have that many observations for each arm. So here, for example, the true parameter is here, and you're kind of shifted away. But we know from concentration theory, from classical like frequency statistics, that we can measure the uncertainty that we have with this estimator. So we know from Hoeffding's theorem that with high probability, the width, like this area between theta hat plus minus some confidence width, we know that the true parameter is inside these confidence intervals with high probability. So the UCB algorithm tells you to do the following. At each round T, compute the mean, compute the upper confidence bound, which is like kind of your optimistic estimate, optimistic proxy for each arm, and pull the arm that has the highest optimistic value, meaning the largest upper confidence bound. And this is actually just saying we want to take into account the uncertainty that we have, so that like if an arm that hasn't been pulled enough, we kind of give it a chance, and this enough is measured by the width that Hoeffding's theorem gives us. So this is like in one slide, the UCB algorithm, which is basically at the base of almost all Bandit algorithms existing. And so we're going to build on this in our algorithm afterwards. So it's kind of an elegant thing, like this kind of finite time control, high probability control of estimator. And it's something that's really recurrent both in RL and in Bandits. OK, is there any question on UCB? OK. So, so that's one thing. But now the problem is that we said that our customers' preferences are changing, meaning that our environment, our theta A's, they are not constant things. So we are going to allow them to change, and we measure the amount of changes by this gamma t budget. So we call it variational budget. The variational budget is the amount of changes that there has been in your environment up to round t. So every time there is an arm that changes mean, I just like count one. So that's kind of a binary measure. You could also measure how much it's changed, or like you know, you can change a bit this variational budget, but basically that's what it is. And then when you pull arm t at round t, you actually observe a reward that depends on the current distribution of the current customer. And now the regret becomes a dynamic regret. So this dynamic regret is at each round, I compare not to a star, because a star doesn't exist. I compare to a star t, which is the current best arm. So that's a difficult objective, because if for example, the arm star t was changing all the time, well, what could I do? Not much, right? Like I wouldn't have time to collect data to actually observe it, but I'm able to measure this with the gamma t. So in the end, what I want to do is I want an algorithm of which I can measure the performance given some budget gamma t. So if gamma t is very big, basically my performance is going to be very bad, but it's not going to be my fault. It's going to be the fault of the environment. So it's OK, and it should appear in my bounds. But the reason why we are interested in this metric is that it's a hard metric, and in the case where it's not too difficult, we can actually give very strong guarantees on the behavior of the algorithm. So that's a bit of a kind of side remark, because some other people may be interested in other metrics. But for us, it's really important that it's a dynamic regret. Yes?
You take the gamma t to be the sum of ones, because in principle, theta t is something that can take different values, right? So why you don't take into account the chain of theta t, or just to count ones?
Yeah, so I mean, that's a good question. For the presentation, I kind of try to simplify the gamma t business as much as possible by having this metric that is like kind of the biggest. It's an upper bound on the metric that you can have. But in the paper, actually, we count gamma t as like the sum of the L2 distances between the theta t's. So if your theta t changes a bit, we still count it, but it doesn't matter. The real problem that you have is when the best arm changes. So like you could also just measure the instance when the best arm actually changes. But I mean, yes, there are several ways of having a variational budget, but this thing is kind of the simplest way of writing it, maybe. So it's a bit of an abuse of notation. Yeah. So what do we want to do when the environment is changing? Well, we cannot keep all the data that we've had so far, because the data that we've collected is obsolete after some point, like after a certain amount of changes. So for each arm, maybe all the things that we have in our history is no longer valid or doesn't represent the current distribution. So what we do is we forget the past. So that's one way. The other way would be, for example, to detect changes and just forget the past when we detect changes. But what we'll do, to simplify things, we are going to say we only keep a certain memory, which is a memory of size W. And this memory is what we judge is still valid. So if the budget is not changing too much, we can still keep a window that's large enough, and that allows us to keep track of the theta hat t for each arm. So that's one way. like non-stationary time series is a very, very big topic in statistics. There are many ways of dealing with non-stationarities. In our algorithm, like it's something you could plug and play. Basically, we chose that method. It's like this windowed estimator. But if you have a better method to estimate, like, you know, non-stationary statistics, then like you could try and plug it in, basically. Yeah, so that's for non-stationary bandit. And what you do is you just play UCB with that, because we can also, like, even with window W, we can compute an estimator, we can compute an upper bound. So you could play just UCB with that. So that's basically what we do in non-stationary bandits. And the problem for us is that we have an additional difficulty, which is that the rewards are delayed. So delays in bandits is also something that happens and that we can control. So it's just saying that basically between the moment you take your action and the moment you can observe the reward, there are D time steps. So for a D step delay, D time steps that are going to happen, and you cannot observe anything. So in that case, the only thing you can do is just look back in time and like look at just like what was the state of the things D steps ago, and you have the data that you have. So there's not much to do actually in delayed bandits when the reward is D step delayed. So in that case, yes, we just have actually this should be a D here, but we basically take the data, we compute estimators, just taking the data that is kind of available at the time. But our problem here is that we actually have both. We have non-stationarity and we have delays. So if we don't have anything in the middle, actually as long as the variational budget, if the changes are just as frequent as D, for instance, like if every D time step it changes, like there is nothing we can learn, and we can easily have a lower bound on the regret that's linear. So yeah, basically, if you don't have anything else, the problem is wrapped and there's nothing to do. But thankfully, we have this intermediate observation. So yeah, okay, I had a little note for the kind of experts in the room about this dynamic regret. So just a parenthesis before I move to our model. In Bandit and in online learning, a lot of people are actually interested in minimizing a metric that compares not to the best arm at each round, like to the A star T, but to actually the best arm in hindsight, like what would have been the best action had you known all the changes of your environment on the way. And this is not what we do. And basically, we don't want to do this because usually these algorithms are a little bit like exploring. And for this type of application, like they are a little bit too costly in exploration for this type of application. It was not really acceptable. But that could be another approach. So just to mention that we are not doing this. We're not studying the regret in hindsight, like the best arm in hindsight. Yeah.
So that'd be quite different, right? Because you would kind of always keep the same action rather than trying to be dynamic.
Right.
In the other case, so I didn't understand quite the comment about exploration as much as I was just pointing my attention to the fact that in your metric, you kind of want to compete against the guy that each instant of time, they have really this knowledge of the distribution, just pick the best.
Yeah.
Whereas here, the objective is really like, so it's much more point-wise. This is much more average time.
Yeah, exactly. Exactly.
You want to be also much more reactive, so to say. So this one seems to be much, it's average out. You just look at it.
Exactly.
Your changes every time, so it's much more reactive. So.
Yeah, exactly. Yeah, exactly. Yes. So exactly, it's reactive. Our metric is reactive. So we really want to follow the customer's preferences. And here, what it is that we would like to kind of try in all directions so that we can kind of measure the average customer preference over time, despite delays and non-stationarity. So we could do that, but it would not be satisfying because customer preferences would change and we would actually never really match the current ones. So, okay, so for our metric, we don't have a solution unless we include the intermediate observations. And this is really the novelty of this work, is to propose a bandit model that actually has state or has intermediate observation. So we propose a MDP, a Markov decision process, for a bandit problem. So we have something that's really at the intersection between bandits and full stack reinforcement learning, where like you have states and actions and like agents that have complex behavior. So here it's something a little bit in the middle, and that we use to disentangle the non-stationarity, which comes from like customer preferences, and the delays that just comes from the fact that the metrics are delayed by design. So what happens is that we model these signals, we model them as states, and we suppose that when we take an action, we first transition to a state that we observe kind of immediately, like whether the user downloads or not the app, we kind of see it immediately, like either they do it or not. And once they do that, once they did it or not, we actually suppose that the reward probability is just a function of the state or the signal that we observed. So in a sense, we separate, we factorize we factor the reward distribution into two parts. First, a probability of transition, and then a reward probability that, given the signal, is independent of the action that were taken. So in a sense, you could take several actions that all could lead to to a certain reward, and give a certain observation, a state, ST, and given that state, there will be a reward that doesn't depend on the action that you've taken. And so doing that, we add data to the history, we add information, and we are going to be able to use this separation to construct estimators for the model quantities. So we are going to adopt a very model-based approach, where in a problem where the model-free approach to RL would actually not work, because we said that like if there is delay and non-stationarity, you cannot estimate the reward function. So what we say is we adopt the model-based approach. That's kind of a distinction in RL. There are people that are more model-free, more model-based, but here like there's no solution. You have to do model-based stuff. So so how do we do that? So that's a bit of literature. This model actually was kind of proposed in a full information setting by Timothy and co-authors before I worked on the problem in bandit settings. And so non-stationary bandits is something that people have studied before, so we really use that as a tool. And the main algorithm that we build on is this UCRL, which is this model-based RL algorithms, which called UC for upper confidence reinforcement learning. So I'm going to describe how this upper confidence reinforcement learning works in our setting. Okay. So how does it work? Yes.
This is the algorithm part, right?
Yeah.
From the way you introduced it was the idea that the reward can change, and if it changes too fast, I'm lost because I don't have time to learn.
Right.
I don't quite see in the assumption I see the assumption you make. I basically say I take an action, observe the state, and then the reward is a function of the state. Right?
Yeah.
So how do I interpret this assumption as somewhat the reward doesn't change too much? I was expecting that kind of assumption. The reward doesn't change too much over time, otherwise I'm lost. Now there is this assumption. Can I interpret this assumption as the research doesn't change,
the reward doesn't change too much? Yes. Yes, the reward, what happens is that the reward itself is only depending on theta t, which theta s now, and this theta s never change. This part here is stationary. We assume that once like the reward given a signal is something that doesn't change. Basically, it's possible that people for a certain time, like people are really interested in like Olympic Games, and they all want to, like download an app about Olympic Games. But like, given that they've downloaded it, we kind of fix the reward probability, or we said that the probability that they actually use it is just a function of they have downloaded it. But nowadays, people don't really want to, download the app, the Olympic Games app anymore, and so they actually would transition to not download it, and then the probability of reward is what it is when you don't download. So it's very close to 0. So this is really the way reward won't change anymore because we block theta s on the second stage. And so, so we're going to see how to apply the model-based RL algorithm framework. So for that, we need estimators. But estimators, we sort of know how to do it because we have a non-stationary part, and we've seen that with Windows estimator, we can estimate non-stationary quantities. And we have a delayed part, and that also we know that we can compute because, you just look at what's available, and you compute the average. So this is what's going to happen. We have the theta t that is just for each state. We have a theta t that uses the available information, and we have a p hat t where p is the transition probability, and that only uses a window W of data, so the most recent transition. And so for each of these estimators, as we saw before, by usual concentration, we actually have concentration bounds, and we're going to see how we can use that, because in the end, what is of interest for us is an estimator on the reward probability given an action, which is, here I noted rho TA, which is this scalar product, or this sum of the PTs times theta s. So I have an estimator for PT, I have an estimator for theta s. How do I compute an estimator for R, for rho, and N confidence bounds? So this is the topic of UCRL, how to construct these confidence bounds. So far, so good with the estimators. Okay, so this is the trick of UCRL. The idea is to choose the best action in the best possible MDP. So MDP, markup decision process, in the best possible environment. So how do we do that? Here I have an example with 3 states, so just the same example as before. So I consider for each action, for some action A, for instance. So for the 3 states, we have a theta hat, and we have a theta hat plus, which is just the upper confidence bound for theta. So like I said, for each theta s, we have a confidence interval, so we know what's the upper confidence bound. We know what is the highest possible reward. So that's for each summit of this simplex. And then for a certain action, we actually have a PT hat, and we have a confidence bound for each direction, which is like an L1 confidence bound. You can also imagine some more fancy confidence area around the probability vector in the simplex. But basically, we have a convex set inside the simplex. And what we want to maximize in our case is a linear function, because for each action, so for each action A, I want to maximize this function where the vector Q is like a variable that belongs to this convex set. So maximizing a linear function in a convex set is something we know how to do. So we just use some simplex algorithm, very, very classic stuff. And what we obtain is the optimal, the best possible MDP, the best possible transition vector. And then we can compute a R plus, which is like the upper confidence for the reward for action A at that round. And we know by construction, actually, that with high probability, this R plus A, this optimistic reward, is larger than the true value of the arm at that round, of the arm A. So here it should be an S. Sorry about that. So yes, so that's this kind of simple version of UCRL. It's really like using confidence intervals and kind of combining them together to obtain a confidence bound on this type of quantities. So now that we have that, well, it's kind of simple. We do UCB the same way as we explained before. We just pull at each round, we pull the arm that has the highest upper confidence bound. So just the highest R plus A, and that's it. And so the good thing is that we can actually have guarantees for that. So these guarantees are bounds on the dynamic regret, where what we did is that we fixed a time t, like a certain horizon t, and then we kind of wrote bounds that depend on both gamma and W, and we said, let's just look at what the bound looks like when we set W optimally. So these bounds are for an algorithm that kind of has the best W, but the choice of W itself, like being adaptive, choosing the right window, is a difficult problem. And it's not addressed by this work. But we can still say a lot of things about the performance of the algorithms. So we have two types of bound. One that is problem dependent, so it depends on the gaps, the changes of rewards, and one that is just worst case. And what we see compared to an algorithm that actually, so an algorithm that ignores the signals, has a term here where the variational budget is multiplied by the delay. So every time things change, like you pay the delay price. So that's why you actually like cannot learn anything. But in our bounds, the delay term is always a constant. It's always a constant that is not impacted by the non-stationarity, is not impacted by t. So this is really where we see the disentanglement, basically, of the non-stationarity and the delay in the analysis of the algorithm. So that's for the theory. But the good thing is that it actually works in practice. So we did some, maybe I can walk fast and slower. So we did some experiments on simulated data. So we simulated an environment where like the probability of transition change and like the reward is delayed and everything. So we have on one hand short delays, 100 steps, and on the other side long delays. And we are going to compare our method, the NSD UCRL, which is the green curve. We are going to compare it with a bunch of things. So we chose kind of strong baselines. The first baseline, the orange one, which looks like the weakest, is actually the UCB that adapts to non-stationarity. So it's the best you can do when you are in a non-stationary environment and you don't know the intermediate observations. So this yellow line looks not that good, but it's actually the best you can do in general. And these two other curves are oracles. So they are a policy to which we actually we tell them that there's been a change. And we are going to impose changes every 2,000 steps. So these oracles, they know there's been a change, so they know that they have to reset. The blue one is just an oracle that plays UCB. And the red one is an oracle that plays our algorithm. But instead of having the window, it just like resets when there is a change and keeps all the information otherwise. So we kind of observe the cost of the window between the red and the green, and we observe the cost of, like, the benefits of having the intermediate signals between the green and the two other ones that are above. And so what's interesting is that in the case where delays are kind of short, 100 steps, actually UCB, the blue curve, does pretty good. Like it restarts every time there is a change, so like it knows what is the best action after 100 steps. So that's okay. But on the long delays, when the delays is roughly half the size of the non-stationary windows, our algorithm actually is the only one that is not an oracle and that actually adapts to the non-stationarity and the delays. Yes, so I had animation to explain you all this, but I think that was kind of, I could just show. So yeah, and perhaps a last remark is that in the end, the cost of the window here is very small. So there's always the problem that like, how do I know what is the window? Like indeed, in my experiments, I kind of set it, like actually I set it to the theoretical value, which is kind of given the variational budget, so I set it to the optimal value. But yeah, you would pay a cost for having a window that's too short or too long. But like, yes, this cost is if you are able to set a window that's okay, you actually have an algorithm that almost behaves optimally, where the optimality here is the empirical lower bound given by the oracle. So yeah, so we were quite happy with that. But then we were like, what if actually like this whole thing is a model, but this model is wrong, like somehow misspecified, or at least like not always valid? So like we wanted to know what's the robustness of this whole thing when there is some perturbation of the model. So the perturbation that we introduced is just saying that for a proportion alpha of the time, like with probability alpha, the reward that is generated is actually just a function of the action, and like whatever observation that you observe has nothing to do with the business. So it's actually a noise. Like it's going to not give you information about the reward function. So we wanted to see what's the amount of alpha, what's the amount of perturbation that we can afford that still allows us for our thing to work. And what we noticed is that, well, there are two cases. Either that distribution mu, that's like the direct reward, actually doesn't modify the best action. It modifies the distribution of the reward, but it doesn't modify the best action. So kind of you can still cope with. And the bad case is when actually like it modifies the best action. Like sometimes in the perturbed model, the best action is another one. So in that case, it means that our algorithm would be learning some dynamics that actually have nothing to do with the best action. So like this is when things get really difficult. So what we observed is that when the perturbation is small, actually, well, compared to UCB, so that's on a stationary segment, like we just run on a stationary phase, and we look at what happens when there are perturbations. Well, on a stationary segment, it's actually still pretty good. It even seems that, like in the bad case, somehow having these intermediate signals can help. So yeah, that's something that's perhaps a little bit strange. But I guess what is difficult for UCB is that the reward distribution is not really complying with the actual hypothesis we make on how the UCBs are constructed. So perhaps there are things that also break UCB here. But generally, the tendency is that both things work, even our algorithm. But as soon as there is too much perturbation, in the good case, we can still manage. So even like if a third of the observations are still kind of off, we can still learn. But if a third of the observations are off the model and it modifies the best arm, then we cannot learn at all. So there are still things that should be researched, and I think we still have that as our little open problem for next works on this. Like it's the question of whether we could identify that our model is being wrong, right? Like if we are learning nothing, maybe we just want to switch back to UCB, like do some kind of model selection kind of on the fly. So this is really something we haven't looked into, but these experiments kind of raise the questions. Right. So I was actually saying half of the slide. So yeah, I think this is, for us, it was a kind of good success story of solving a problem that's like something real. So it's a success story up to a certain point. Like we actually patented this idea, but we couldn't really get to implement it and like have it work even on a simple system. So this is like, yeah, bad luck. This is like just difficulty of collaborating with We've applied teams that have very, very short schedules, and like for them, it's really difficult to like. I come with a MaLGa algorithm on their desk, and they're like, "Yeah, sorry, I already have a lot of things to implement. Sorry." But like, yeah, we're still working on it, and it's an idea that really is ubiquitous. Like it's really everywhere in a lot of systems. So we are still hoping that someday we can make impact. But otherwise, yeah, I think from just a theoretical perspective, from like, let's forget the beautiful story of solving a real problem. Just from a theoretical perspective, I think that's like having a model that's somewhere in between Bandits, which is like a very simple problem, and RL, which is a very hard problem. I think it kind of brings insights. It's interesting to also like discuss what's like the difference between learning in a model-based way and in a model-free way. So there are lots of, I think this model by itself could be used like as, you know, an alternative way of studying online learning problems with intermediate observations. And so we hope that we can, for example, answer the question on model selection, and also like try to see what happens if we introduce context, if we introduce like contextual information, either about the information, the intermediate observations, or about the actions. So yeah, I think there are a bunch of things to try. And perhaps one thing that is mentioned here, yeah, and that I haven't really said when I showed the results, like the analysis, is that actually this whole window thing that I've been kind of hinting at is not the optimal thing you could do. And our worst case regret bound is actually not optimal. And we would hope that, you know, by plugging in a solution like a non-stationary algorithm that's actually more efficient, we could actually get the optimal rates in the worst case as well, which is not the case at the moment. So yeah, I think with that, I will finish, and thank you for your attention, and please, I welcome all your questions. Thanks.
There are questions, maybe? Sorry. We should use this one so that people also on YouTube can follow. In the meantime, okay. Okay, I had a curiosity about the dependence on W. So you mentioned the choice of W is tricky, and I perfectly understand. But do you know how the bounds depend on W? Do you have I don't know, how do you choose the optimal one theoretically?
Yes, so basically, every time you reset, every time I can probably show this. So every time here there is a reset, it kind of takes a window W to grow a new collection of data that is good. So you pay W as kind of a function of the gamma, like it's the gamma, and you basically have a cost that's something like of a gamma times W. But then you also have, as much as you have data, like as if W is very big, you also have more data, so your estimators are more precise, and so there is a 1 over square root W that's somewhere, and so like basically, like when you optimize this, when you do this, the balancing, you have a W that's like something like gamma, square root gamma, or something like this. So this is how, this is basically how the regret bound is proved in like 2 sentences. It's like computing how much error you make based on the changes and the W that you have. Yeah.
Thank you. Other questions?
A couple of questions. So the first one is the first one is so you discussed image specification in plots. I was wondering if it's also part of theory.
And so no, unfortunately we.
If you think one can do it, like kind of try to see if quantify how much because it's like it's not the model is completely wrong. It's like
it's kind of
up a little bit. So you think one can quantify because one can have scaling of how much alpha has to be before it destroys everything and so on. So is it possible to think to that bounds?
So at the moment we haven't done it. So the story is that we actually like had everything for the paper, and then last minute someone at a meeting was like, hey, by the way, what if? So I just ran experiments, and then we were like, okay, so actually there is something there. But we don't have the theory at the moment, but it's really something that we've been discussing. It's a problem of, it's really a problem of model selection, but like online. Bandit model selection is a topic that has actually been very active in the literature for the past year or something. So it was at the time when we finished, it was a very open problem. There is more results now, and I would really hope. I think there is a theory that you could make about like if the model is that much imperfect, you can actually do that well or that bad. And also, I think this whole like good case, bad case is very ill specified in my slides, and also like in general, I think there is like, characterizing what is a good case and a bad case. All this is interesting also for this question of model free versus model based. Like I think it's a philosophical question in RL, and there's really a split in the community between the people that really strongly believe in model based, and that usually are people that come more from physics and that are looking at problems with obvious, physics models that they know they're right. And the people that, like, for example, Dave Silver, that work on AlphaGo, and there's no physics, and he's happy to not have models because he just wants to know what's the reward for an action. And so here, this very simple toy problem actually gives a nice playground to play with these questions. So it's really something we are discussing, but I have no results to report right now. But there are interesting questions there, yeah.
And I guess the other question was, so you said it, so far it's not working as you hoped yet, but so if you have to point the finger, what do you think is who's the guilty? Is the window, or is the windowing, or something else? Do you think there is something particular? What is the first place you would put your finger?
So yes, this non-adaptive window. So at the moment, the window is a constant. I choose it as a hyperparameter at the beginning, and that's it. And I cannot, like if I don't have data at the beginning, like it is in online learning, I actually don't have a good way of choosing the window. So, but this is not a lost cause because, I mean, there has been a lot of work on non-stationary problems, and especially in bandits. There are recent works, I think, called 2020 or something like this on non-stationary bandits. But basically, the idea is to have adaptive windows or resetting, like restarting algorithms that detect changes. So change detection is also like a very well-known topic in statistics, but like you can also do it in bandits. It's a bit more tricky because there's the exploration, exploitation that also impacts you in the background. Like basically to detect changes, you need data. So, but to have data, you need exploration, and exploration costs. So there's this really, really like very tiny balance to find where you have just enough data to do the change detection. Turns out the change detection is very, very like accurate. Like it's actually a kind of easy thing. Like it costs log, and we actually don't bother too much about the logs. So there is a way, and which is basic. I think the best way would be to just do change detection, and then restart when there is a change that's detected. But that's if you assume that this non-stationarity is not structure at all. Like basically, if it's a cycle, if it's like arm 1, then arm 2, then arm 1, then arm 2, maybe you don't want to forget. You don't want to reset. You want to keep in memory things. But then it becomes like really difficult. Like if there is the memory that comes into the game as well, then it's another game basically. And I don't really know what you could get in that case. I'm not sure exactly how you would write this, but for sure, if you realize that it's a periodic, the rewards or like the transition is a periodic series, like you don't want to forget what was happening last week because it's the same. So yeah, these are the different possibilities.
Other questions? I had another curiosity. You told that you are studying this dynamic regret in the sense you change the optimum, so so you compare to the optimal action at each time, but and not studying the other one, but it is an upper bound, right, of the other one. Or low, I don't know, lower, upper, somewhere, in the sense that you're comparing the best at each step with the best static one, so this difference should be bigger, the thing that you study should be bigger than the other one.
Yes, it's bigger, like it's a harder problem.
Okay.
Yes.
Yeah, so if your bounds apply naturally also to the standard regret analysis. So,
Exactly.
okay.
Exactly. So I think yes, that's the thing. You could get better bounds, kind of naturally. So basically, if you're just looking at the best in hindsight, the bandit theory already tells you that you can have a square root t regret. And for us, getting a square root t regret actually requires to go through this like very complicated, like this very adaptive, non-stationary. For now, I have t 2/3 bound. So like my bound is not as the square root, and this is the fault of these constant windows. And if I work hard, I could probably make it a square root, which actually, so like, which would be the optimum, because we know from the bandit theory that like we actually have a lower bound on that other metric, the one that you were asking for. So this hindsight regret, we know that there's a lower bound on square root t, and it's smaller than ours. So we know that the best would be square root t, but we don't have it yet.
Yeah, but you think it's possible?
Yeah.
Then it behaves the same way.
Yeah.
Thank you. So, other questions? Last chance? Maybe we should check Slack. Could you, please? No? Okay. Okay, so thanks again
Thank
for
you.
the very nice
Thank you
and
very much.
interesting and clear talk.
Thank you.